All right, now we're in the home stretch of Chapter 4, dealing with ions and isotopes. So when we're looking at those elements on the periodic table, we're looking at elements in what we call their neutral state or their ground state, where they have the same number of protons and electrons. But those are not the elements that are going to be in the reactions. They're not going to react exactly as we see them in the periodic table. What's going to happen is, during the chemical reaction, an atom will often either lose or gain electrons, and in the process they become these charged particles that we call ions. Okay, very important to us, ions. Those are what are going to react. Now, if an element gains electrons, let's start with loses, okay, since that's what's next in the list. If it loses electrons, it becomes positive, right? If it loses electrons, it now has more protons, positively charged particles, than it has electrons, negatively charged particles, okay? So it becomes positive, and we call that a cation, okay? Pronounce that cation. If it gains electrons, it now has more of those negative charges than it has positive charges. So it is overall a negatively charged particle. A negative ion is known as an anion. Very important to remember cations and anions. That's what we're going to be looking at in lab at the end of this week. Now, when we look at the symbol, the way we write the symbol for an ion, we always show the charge in the upper right corner of the symbol. We write the symbol from the periodic table, and then we write the magnitude of the charge, and then the sign of the charge, positive or negative. So if we look at examples, magnesium tends to lose 2 electrons, and in the process becomes this positively charged. It now has 2 more protons and electrons. So we write Mg for magnesium, 2+. Just a reminder that by now you need to start looking at that periodic table and be able to recognize elements from the periodic table. You need to start memorizing those. Oxygen tends to gain 2 electrons, and then we would write O and then a 2-, and we write it as a superscript so that we know that that's the charge for that particular ion. These are written as ions. So let's look at an example of making an ion from an element by losing electrons. Now, it's a little bit confusing because when we lose electrons, we end up with something that's plus. We usually think of losing something as subtracting or taking away, but in this case, when we lose electrons, now we have extra positives. So we're a positively charged particle. If we look at lithium, lithium atoms tend to lose an electron and form a lithium 1+ ion. Now, we represent this by writing an ion equation. So we start with elemental lithium, just the symbol as we see it on the periodic table. When we see this, we're presuming that the number of protons and electrons are equal, and this breaks apart, yields a lithium cation plus 1 electron. So we represent an electron as the letter E with a superscript of just a -1. The charge of an ion is going to depend on how many electrons were gained or lost, and there's a formula that we can follow for that. The ionic charge will always be the number of protons that you have in the element minus the number of electrons that you have. This is after electrons have been gained or lost, after the electrons have shifted. So this is the symbol for a proton, P with a superscript of a plus. This is the electron, we already mentioned that one. So for the lithium 1+ ion, it started out with 3 protons and 3 electrons. It lost one of them, so it has 3 protons and 2 electrons. 3 minus 2 is a +1, so that's where we get that +1. Now, if we look at it in the other direction, let's look at a fluorine atom. A fluorine atom tends to gain an electron to form fluorine anions. So here's our elemental fluorine. Now we have the electron on this side because we're gaining it. We're adding it to the fluorine. It becomes a fluorine 1 minus. Okay, again, same formula, number of protons minus the number of electrons. Everything's the same here. So now we had 9 protons, and now we have 10 electrons. We gained an electron. So the charge is going to be 9 minus 10. That gives us a -1 charge. Now you don't have to use this formula every time. You'll start to be able to look at elements and look at their position on the periodic table and know what the charge will be. Now that doesn't work necessarily for those transition metals that we have in the middle, but for the main group elements, you can predict what sort of ion they're going to form by looking at where they are in the periodic table. All right, so remember that number that was associated with the letter A at the top of each main group column. Again, as you're going through these slides, it's a good idea to open up your book or pull up a figure of that, use that printed copy that I gave you, and look at these things as we talk about them. So looking at those main group numbers in the periodic table, 1 through 8, that is going to tell you something important about those elements. It tells you the number of what we call valence electrons for those elements. Now, we haven't looked at the overall electron configurations, what we're going to call it, of these elements, but just know that valence electrons are going to be the electrons that are furthest away from the nucleus in an atom. They're the outermost electrons. So if you remember the description we had of the shape of an atom where the protons and the neutrons are in the massive nucleus in the center and the electrons are some distance away from that. Well, not all electrons are equal distant from that center. So the ones that are furthest away from the nucleus are actually the ones that have the least attraction to the center. If you think about it, the further away one magnet is from another, the weaker the pull. So the electrons that are on the outside are the easiest ones to move. And that's where we get this gaining and losing of electrons. We're going to do it with those outermost or valence electrons. That number is the key to knowing what kind of ions form. So I can predict the charge acquired by an element based on that valence electron number, the column number for main group elements. Main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. Now remember, the noble gases are the ones that are furthest to the right on the periodic table. They're the very rightmost column, the group 8A. Okay, so what are we talking about when we talk about that? So if we look at the ions, okay, and their position in the periodic table, we can see, for example, here's the 8A. All right, here is 7A. Now, they are one step away from 8A. And if I can move this way, move to the right toward 8A, that would be equivalent of if I can gain an electron. So everything in group 7A tends to want to gain one electron, which takes them one step over to that last column. Now if I look at group 6A, I have to go 2 steps to get to that column. These all tend to form -2 ions. I look at group 5A, it has to go 1, 2, 3 steps, so they form 3-. And they haven't shown every element here, but that pretty much holds down the column. All right, now group 4A, notice they haven't written anything in here. Theoretically, you could go 4 steps this way, 1, 2, 3, 4, and I could get there. But the thing is, when I get to 4A, this is kind of a middle point because I've been going this way, forward toward 8A, but I could also back up. I could, go forward to the one that's nearest, or I could back up to the one before it. So if I look at 4, 1, 2, 3, 4 forward to get there, but I could also go 1, 2, 3, 4 and back up. So theoretically, it could be a 4 plus, a 4 minus. We find out that it doesn't tend to do either. Group 4A does something else, and we're going to look at that in Chapter 5. So keep 4A in mind for now, but don't worry about that one. No ions here. All right, now Group 3A. I could step forward 1, 2, 3, 4, 5. I could add 5 electrons to get over there, but that's a lot of work. I can back up a lot easier. So if I'm right here, I can go 1, 2, 3, and back up to the noble gas that came before it. I can lose 3 electrons. If I lose 3 electrons, now I've got a 3 plus charge. So 3A forms 3 plus. Don't worry about transition metals. They do something a little bit different. Here's 2A. I can go forward 6, but it's a lot easier to back up 2. 1, 2. So these all form 2 pluses, and then everything in column 1A, I just need to back it up 1. Back that one up to there. Rubidium, I can back it up to here, so on and so forth. So I can back up 1 pluses. So just remember 1A, 1 plus. 2A, 2 plus. 3A, 3 plus. Skip 4A. 5A, 3 minus, 6A, 2 minus, 7A, 1 minus. So here's my dividing point at 4, and I go 3, 2, 1 negative, and then 3, 2, 1 positive. Now, just a little side note, the reason we don't have the transition metals in here is because they don't tend to form ions based on their group number. They form cations. So you're going to see positive charges. These are metals. Metals form cations, but they don't always form the same cation. So the transition metals, depending on which one you're looking at, you may get a 1 plus, a 2 plus, a 3 plus. It can form any of those depending on the situation. There are 2 exceptions to that. Silver is always a 1 plus, so that's Ag if you want to circle that one on your periodic table. And then zinc, which is Zn, that one is always going to be a 2 plus. Those are what are called invariant charges. They don't change. So you're never going to see an Ag 3 plus or a zinc 1 plus or anything like that. Now, it's not based on their group numbers, though. It's obviously, if you look on the periodic table, silver is not in group 1b, and zinc is not going to be in, well, silver is in 1b, but that's not why it's there. It's not based on that. So 1b, 2b, copper doesn't tend to form 1 pluses, and then gold doesn't tend to form 1 pluses. So you can't use the group number on that. But do remember, silver, if you see that one, it's always a 1 plus. Zinc is always a 2 plus. Those are invariant. All right, so now we're going to look at another aspect of the elements of the periodic table and the ions, and that is when you get something called an isotope. Now in ions, this is where the number of electrons changes. We gain or lose electrons. With an isotope, this is when the number of neutrons is going to vary from one atom to another. Now, we've already stated that if we have an atom of a given element, every atom within that element is going to have the same number of protons. That is what defines the element. That's what gives its characteristics. So you're never going to have, say, a sodium atom that has 12 protons. If I had 12 protons, I would have magnesium. I wouldn't have sodium. Or I could have oxygen. Oxygen has 8 protons. I'm never going to have an oxygen with only 6 protons. That would be carbon. Okay. So protons is fixed, but the number of neutrons is not always fixed. Elements are not defined by their number of neutrons. So if I have an atom that has the same number of protons, 2 atoms that have the same number of protons, but different numbers of neutrons, these are what we call isotopes. They're both atoms of the same element. So if I have 2 oxygens, they're both going to have 8 protons, but one of them may have 14 neutrons, one of them may have 16 neutrons. Those would be isotopes. Now the interesting thing about this is that every element has its own unique percent of what we call the natural abundance of isotopes. So there's a certain number of isotopes, and that varies. Some elements will only have 2 or 3. Some of them may have 4 or 5 or possibly more. But it is unique to that particular element. And the number of isotopes that you have and the abundance of those isotopes are what define what we call the atomic mass of that element. Now remember, on the periodic table we looked at earlier, there were 2 numbers on there. One was the atomic number at the top that defined the number of protons in the nucleus of the atom. 1, 2, 3, 4, 5. Those are the ones that count up. But then there's another number on there that's a fraction. So if we look at hydrogen, it's 1.01. Or if we look at lithium, it's 6.94. What are those numbers? Those numbers are based on these isotopes and their natural abundances. So for example, neon. If I take a naturally occurring sample of neon, I go to one of these glowing neon signs, and I take a sample of the gas from that sign. If I could break that down into all the various atoms, all the various isotopes within that, I would find 3 different isotopes. Excuse me. One of them is neon 20. So this would have 10 protons and 10 neutrons. The 20 is the sum of protons and neutrons. So always 10 protons, but now 10 neutrons. I also have neon 21, where I have 10 protons and 11 neutrons, and then neon 22, where 10 protons and 12 neutrons. So just a slight variation in the number of neutrons. Now, if I look at the abundance of those, most of that sample is going to be neon 20. It's going to be that first one. And it's not always the smallest that's most abundant. It can be different, but in this case it happens to be the smallest one. 90.48% of that sample will be neon 20, but then I'm going to get 9.25%. That's neon 22, the heavier one, and then only about 0.27%, a very small amount that's going to be neon 21. Okay, so that's how the abundance breaks down. How do I represent that? Okay, so if I'm talking about isotopes, I need a symbol notation in order to know which isotope I'm talking about. And this is the generic format for an isotope. We always put the chemical symbol here in the center, the larger value, and we represent it generically as an X. You'll put in whatever the element symbol will be. And then we will put the mass number in the upper left corner. Okay, mass number, remember, is represented, mass number is represented by the letter A, and then we've already looked at atomic number, that's represented by Z. Now this is a little confusing because we're putting the smaller number on bottom, and in the periodic table they tend to put that on top. But just remember, this is number of protons here, Z, and A is number of protons plus neutrons. So if I were going to write the symbols for all 3 of those isotopes of neon, I would put the symbol for neon, Ne, and then I would put 10. Notice every one of these, neon, and then the 10 at the bottom, 10 protons. That never changes for a particular element. So this is actually a little bit redundant. This information, the 10 and the neon, if you know one, you should know the other. That doesn't change. But then this is the one that changes. Am I talking about the one that has 10 neutrons, 11 neutrons, or 12 neutrons? So 20, 21, and 22. Now the other thing this does, one of the reasons to write in the number of protons is that if you want to know the number of neutrons, it becomes very easy. You just subtract the 2 numbers. So 20 minus 10, I got 10 neutrons. 21 minus 10, I got 11 neutrons. 22 minus 10, 12 neutrons. Okay, so I tend to get ahead of myself a little bit on these slides. Here's the slide that talks to you about that. So the addition of these 2 numbers, gives me the top number. So they're taking the difference, 10, 11, and 12. All right, now Again, I said that putting in the atomic number, the Z value, tends to be a little bit redundant. So there is another way to write isotopes, where you just write the symbol dash and then the mass number. Because again, the chemical symbol, if you've got a periodic table, you can look to see how many protons. So if I were using this alternate notation, I would write the neon isotopes this way, either the symbol, neon 20, 21, and 22, or I could write out the whole name, depending on the mood I was in and how much clarification I thought I needed there. All right, now let's look a little bit at those atomic mass numbers, that decimal number on the periodic table. We said that it's the average mass of the atoms, the isotopes of an element. So how is that calculated? We want to look at a quick calculation of that. Now, if we take chlorine as an example, chlorine has two naturally occurring isotopes, chlorine 35, okay, and chlorine 37. Now, 75.77% of a chlorine sample, if you had a sample of chlorine gas, 75.77% is going to be chlorine 35, 24.23% is going to be chlorine 37. Now, look at what they have here in parentheses. They have mass of 34.97 AMU, atomic mass units. Okay. Now, notice that it's not quite the 35 that it adds up to. So an atomic mass unit we already looked at a little earlier. It's a little bit different from just number. It's dealing with the actual atomic masses relative to something else, in this case carbon. Okay, so if we know the mass of the chlorine in these atomic mass units where we're ratioing the mass to that of carbon, and then for chlorine 37, 24.23% of it has a mass of 36.97 atomic mass units. So we would need to know the atomic mass units, but if we have that, we can calculate those numbers from the periodic table. I take the percent as a fraction, so remember percent, I move it over 2 decimal places, so 75.77% is 0.7577 right here. Multiply that fraction times the atomic mass units, 34.97. Now do that same thing for the next one. So 24.23% becomes 0.2423. Multiply that by the mass, 36.97 atomic mass units. When I multiply those two numbers out and then add those products together, I find an atomic mass of 35.45 atomic mass units. Now, if you look on the periodic table, that's the number that you see for chlorine, 35.45. So in general, if you want to calculate the atomic mass of any element, you will need to know the fraction of each isotope and the mass in atomic mass units of each isotope. All you do is multiply that fraction, so take the percent and turn it into a fraction, times the mass for isotope 1, 2, 3, however many you have, just add those together. So let's look at an example problem of that. Here's gallium. Very interesting element on the periodic table. I believe we've mentioned this one before, but this is the one that melts at body temperature. So it is a solid at about 96 degrees. You get it up to about 97, which is just about body temperature, turns to a liquid. Now, gallium has two naturally occurring isotopes. We've got gallium-69 that has a mass of 68.9256 atomic mass units, and a natural abundance of 60.11%. Gallium-71, here's the atomic mass units for that one, 70.9247, natural abundance of 39.89%. So what we want to do is calculate the atomic mass of gallium. Now, if you're asked to calculate atomic masses of an element, you can do the calculation and then double check yourself by looking at the periodic table. Atomic masses for elements are all given in the periodic table. All right, so let's look at this. What are we being asked to do? We're being asked to calculate an atomic mass. To do that, I need to know the mass coming from each isotope. So I have two isotopes. Here's the first one, the mass of it. Here's the abundance of it. So I just need to change this to a fraction, move the decimal point 1, 2, multiply these two numbers together. Do the same thing for the second one. Here's the mass number. Here's the percentage, change it to a fraction, multiply those two. Whatever the two numbers are that I get when I do those multiplications, add those two together. So here's the first part. I'm going to convert the percentages into the decimal form. Just divide by 100. So 0.6011. 39.89 becomes 0.3989. Now I'm going to take those two numbers and I'm going to multiply them by those atomic mass units. Here's the 0.6011, 60.11%. Here's the atomic mass units. Here's 39.89%, 0.3989. And here's the atomic mass units. When I multiply these two, I got 41.43 about atomic mass units. Here I got 28.29. Now notice we are not rounding these according to significant figures yet. We want to avoid rounding errors, so we've just carried the numbers down a little bit further. Add those two together, 69.7231. Now my final answer I round off to significant figures. I did a multiplication here. I had limited to 4. This limits me to 4. They are both going to have the same number of places here. So that gets cut off at this point to the 4. Now be aware that some isotopes are going to be the radioactive. So when you talk about things that are radioactive, these are isotopes of elements that do not have stable nuclei. So what's happening is that the atoms are going to emit a few energetic subatomic particles from their nucleus, from their center. And when they do that, it changes them into a different isotope of a different element. They actually lose not only neutrons to change isotope, but they can lose protons too and convert into different elements. This is radioactive decay. Okay, so the particles that get emitted by these radioactive isotopes, that's your nuclear radiation, and the isotopes that emit them are called radioactive isotopes. So we're familiar with that term, but you may not have been aware of where that was coming from. And that's what's going on. And now that's the only part of chemistry, really, where reactions are dealing with more than just a movement of electrons. For most chemistry, for most chemists, chemistry involves the movement of electrons with the nucleus kind of remaining stable. But when we're talking about nuclear chemistry, we're talking about changing the fundamental nature of the element that we're dealing with. We're emitting particles that are changing protons and neutrons. So pretty interesting stuff there with nuclear chemistry. All right, so where do we see these radioactive isotopes in the environment? Well, we know that nuclear radiation is harmful to us as human beings and to other living organisms. And the reason for that is because these particles that are being emitted from the nucleus of these atoms are energetic enough to interact with and damage our DNA, our biological molecules. So it's not that the material is inherently harmful in and of itself. It's not harmful to the earth at all. It is harmful to biology. That's where the problem comes in, because we are biological creatures. So how bad are these radioactive isotopes? Well, it depends on the isotope. Some of them, like lead-185, emit very significant amounts of radiation, but they're very short-lived. So if you have radioactive lead, it can do a lot of damage, but only for a very short amount of time. So as long as you're not within range, it will decay fairly quickly, and then you don't have to worry about it. But then we have others such as plutonium-239. Now these have a fair amount of radioactivity, and it lasts for a long time. Their decay rate is very, very slow, and they can last for thousands or millions or even billions of years. So if you have some time sometime, check out this YouTube video that's linked here. Now, again, it's not necessary for class. Don't check it out unless you have some spare time, because it's about a 17-minute video. But it's a really nice look at plutonium and how plutonium is used within the nuclear energy industry, and just a little bit more about those radioactive isotopes. So again, if you get a chance, check it out. Now, there are some beneficial uses to radioactive isotopes, and for those of you who've ever worked in any sort of medical industry, you know this already. There's a lot of beneficial uses to radioactive isotopes. So, for example, technetium-99 is very often given to patients to help with diagnosis of disease, because the radiation being emitted, it's a very low-level emitter, and it emits at a low enough level that doctors can image the internal organs, or they can detect an infection. They can see something that's different that way. Sometimes it's used as treatment for disease, so you can use low levels of radiation to target, for instance, cancer cells. Use a very targeted level there. And there's always nuclear energy on a larger scale. There's lots of pros and cons there, but overall, you do produce a large amount of fairly efficient energy using nuclear radioactive sources. All right, so that wraps up Chapter 4. You do have learning objectives and sample problems within the chapter, so do take a look at those. And we will then go into Chapter 5, and we will start exploring the periodic table and some of the reactions of putting elements together in more detail.